Yeah, over to you.
Yeah. So it gives me immense pleasure to introduce you all to our first speaker of the first invited talk, Dr. Neha Prabhu. She is currently assistant professor at Sai University, Chennai. So uh, we had asked her, and she deliberately agreed to give a talk. And thank you for the kind gesture, ma'am. And most important thing is that herself is MTDS alumni, and if time permits, we can sometimes I will ask our team to have a talk with you. What was your experience with MTTS Trust? So over to you, ma'am. You can start. Yeah.
Okay. So am I audible and is the screen showing my talk?
Yes, yes.
Okay. Okay, so this is something I've been working on by myself, and it's very dear to me because I think it's probably like maybe the only project I started working on purely because I was interested in it, not because it's follows from someone else's question or something like that. And it's been a lot of fun. And it has the added benefit that I can talk about it without having too many prerequisites needed. In fact, almost nothing. If you're a master's student, you should be able to follow this stuff. So let's begin. So the story starts with difference graphs. Okay, so I'm going to be connecting something in number theory to graph theory, but for most part, it's going to be talking about things in graphs, and then we bring in some algebra, so how the graph is defined and so on. Okay, so we start with the finite abelian group, and we view this additively. And okay, I don't see that coming through. Okay. Okay. So it'll be additive. So this is the operation that I'll be viewing my group with. And you take a subset of G such that it has some K elements, any K element subset. Then you can associate to this graph, to this group a graph as follows. So the vertices will just be the elements of G, and the edges will be G comma G plus S. So every vertex G is has neighbors G plus S for every S and S. Okay, and the reason this is called a difference graph is because if you take an edge, the difference of those two elements, which represent the vertices, are lying in your set S. Okay, so that's why this is called a difference graph. And as always, when you learn something new, we should work out an example. So let's look at a simple example. Okay, so I'll take Z mod 4Z as G, and maybe take two candidates for S. It will be relevant for what's coming next. So let's S1 be just the set 1. Okay, and we'll draw the graph. So my vertices are the group elements. So just say 0, 1, 2, and 3. And the edges are given by G plus S for every G. So these are the start and end points of each edge. So from 0, I go to 1. From 1, I go to 2. From 2, I go to 3. And from 3, I go to 4, which is the same as 0. So that's just my difference graph in this case. Okay, suppose I take S2 to be a little more interesting. So I take 1 and 3, say. Okay, so again, I have my graph, the vertices. So 1 will be the same thing. It's just a cycle. Takes me there. But then when I want to use 3 as, add 3 to every vertex, I get, so 0 to 3 brings me back here. 1 to 3, 1 plus 3 is 4. 2 plus 3 is 5. So that's identified with 1. And 3 plus 3 is 6, which is identified 2. Okay. So now you notice in this graph, every edge, every vertex has two edges going back and forth. So because all these edges are like that, so between 1 and 2, there's one going from 1 to 2 and the other one going from 2 to 1. So we just identify these. Okay, so we'll just instead make the graph look simpler by just removing the arrows. Okay, so this becomes an undirected graph. So two directed edges identified as one undirected edge. Okay, so if it's something like that, so this thing becomes just that. Okay, so fair enough. So I hope it's clear what these graphs look like when you take some simple examples. Okay, so what was unique about, what made the fact that this became an undirected graph was because this is a symmetric set. Okay, so this set is symmetric in the sense that whenever little s belongs to your set, minus of that element also belongs to that set. Okay, which is not true for here. This is just a one element set and it's not its own inverse. So additive inverse. So you have edges going only one way. Okay. So, but maybe I'll come back to this later. Okay, so what do we do once we have graphs? Well, one thing you can do to study the graph is to look at its adjacency matrix. So the adjacency matrix of a graph is you draw the matrix where every vertex is represented by each row and column. And there is a 1 if at the ijth position, if there's an edge from I to j. So I'm looking at it as a directed edge, and it's 0 otherwise. Okay, so for this graph, so what will be the adjacency matrix here? It will be, so I have 0, 1, 2, 3, 0, 1, 2, 3. So there's an edge from 0 to 1. There's an edge from 1 to 2. And there's an edge from 2 to 3 and an edge from 3 to 0. And everything else will be 0. Yeah. And similarly, if I do it for this one, now I have more edges. So there's one from 0 to 1 as well as 1 to 0. So 0, 1, 1, 0. Sorry. 1, 3. And then something else from, okay, 0 goes to 3 as well. Yeah. So, and then 1 goes to 2. And 1 goes to 0. 2 goes to 3. And 2 goes to 1. And 3 goes to 0. And 3 goes to 2. Yeah. Okay. So then I fill in everything else with zeros. And here I have my adjacency matrix for this other graph. Okay. Okay, so just as an MTTS style, we try to just observe, look at properties, see what we can come up with. Just, of course, this is just one graph. You ideally need to draw many examples to see a pattern emerging. But one thing we do notice is that this one is symmetric. Sorry, this one is symmetric. And this one is not symmetric. And this is directly connected to the fact that the S in this case was symmetric. The set using which we've drawn the edges. And here in this case, it is not. Okay, S is not. So That's not a coincidence. So as it's not hard to prove. Okay, just a little bit of writing down what Aij should be and having an edge between ij and ji will provide that. Okay. Okay, so this is what I was saying. So if S is a symmetric set, then whenever S is in S, we have G comma G plus S belongs to E. And if minus S was there, I can subtract S. So I start from G plus S and subtract S to get the endpoint as G. Okay, so since these both are in the edges, you always have an edge going both ways between two vertices. Okay, and in this case, the matrix is symmetric. Okay. So what is interesting to in the area of spectral graph theory? Okay, so this is something where completely what graph theory people like to do. So number theory hasn't come in yet. What are the eigenvalues of A? Okay, so if you have a matrix, okay, it's coming from a group, that's great. What are the eigenvalues? Well, firstly, we notice that this is a regular graph. Okay, so a regular graph is a graph where every vertex has the same number of edges, either incident or coming out of it. Now, this is the convention. So if you have, in this case, even though it's symmetric and one is not, the number of edges in this graph, for example, is not seen as 4, but it's seen as 2. Okay, so there are always two edges between two vertices going in opposite direction. So you identify them and you just see the in degree or the out degree. You don't add them up and make this 4. So the degree of this graph is 2. Oh, sorry. The degree is 2 here, and the degree is 1 here. Okay, and that's just the size of the set. So here S1 has size 1, that's the degree, and here S2 has size 2, and that's the degree here. Okay, so it's pretty I mean, that's evident from even the definition, right? So we are taking G is connected to as many elements as there are in S, and so it should be the degree of your graph. Okay, so if there are five elements in S, then every G is connected to five different elements. So you have the degree to be the size of S. Okay, so coming back to the spectrum. Now, in a regular graph, K, the degree K is always an eigenvalue. Okay, and you can check that it comes with okay, it depends on whether the graph is connected, but it's very easy to come up with the eigenvector. If it's a connected graph, it's the vector just 1, 1, 1, 1, 1. Okay, so you look at your adjacency matrix, it'll add up all the edges that are going out of it, and so that'll be the out degree, which is K. Okay. Okay, so if we focus on difference graphs, we get something more. Okay, that'll give you, so the property I just told you gives you one eigenvalue. That's true for any regular graph, no matter what it is. But we have more structure. We know that our graph comes from this particular group, and it turns out that the characters of G give you the eigenvalues. Okay, so how does that happen? Well, you take any character. So character is nothing but a group homomorphism from G to C cross. Okay, so since we are viewing this with the addition as our group operation, so we have G1 plus G2 here, not G1 dot G2. But on this side, we have C cross, so it's chi of G1 plus times chi of G2. Okay, so any map that satisfies the fact that it's a group homomorphism here is a character. And just a fact that if you have a finite group, you'll have as many characters as there are elements in that group. So, and when we're in the finite setup, so everything is good. Okay, and what happens in this case? Well, we remember we had taken this set S. You pick any character and you sum over the elements of S by applying chi to each element, and that becomes an eigenvalue. And every eigenvalue is of this form. Okay, so if G is of size n, then you get an n by n matrix. So you have n eigenvalues, and each of them come from a character. So chi1, chi2, and so on till chi n. These will be the distinct characters of G. Maybe this will be like the trivial one. So the trivial character is where chi of G is just 1, okay, for all G. This is the trivial one, but then you have others, which will be going to roots of unity. Because it's a finite group, you know that G to the n will be 1 at some point. So you need the image also to satisfy that condition. Okay, so basically, even if you've not seen characters before, that's fine. But if you just treat it as a homomorphism, and knowing that finite groups have as many characters as the size of the group, it's easy to see that you're only looking for n eigenvalues, and it's actually given in this form. Okay, but why is this true? So every talk should have a proof, and this is it's not something obvious, so I felt it'll be nice to show a proof. Okay, so let G1 to Gn be the elements of your group. Let X be the column vector where the ith component is chi of Gi. So it's this vector here. Then, so my claim is that summation, we want finally that summation chi of S belong to S, should come out as an eigenvalue. Okay, so the ith component is just Aij xj, usual matrix multiplication. But here my xj, the jth components are given here. So it's just chi of gj. But what was the definition of the Aij? It is 1 if you have a edge from I to j. Now these are difference graphs, so that will mean that gj minus gi should have an element from your set. Okay, so G comma G plus S was the edges. Okay, so the difference of these should be an element of S, and that's what I've written here. So it's just applying, it'll be chi of Gj, and in that case the Aij is 1. Okay. But this is nothing but, so I'm just rewriting Gj minus Gi as, okay, just do the reverse. Take an element S in S, and then for each I, you're looking at all the neighbors. So here, see, Gi is fixed. You're looking at all the neighbors. So the neighbors of Gi are, of course, just Gi plus S. And so you get this sum. But now you use the additivity of chi to say chi of S plus Gi is chi of Gi times chi of S. And you get the sum nicely popping out. Okay. So this is this doesn't change with our indexing. So the Gi is fixed, and that's nothing but the ith component of this vector. Okay, so that's xi. So put together, so start to finish, we prove that. So this happens for each I, and finally we get that Ax is this the same value times x, and this completes the proof. So any questions? If there are any, I'm told that I speak a little fast sometimes, so please feel free to stop me. And if you didn't follow any part of the talk. Okay. Okay, so now we will focus on a specific group coming from finite fields. Okay, so let Q be a prime power and N be a natural number. And you look at FQN, so the nth degree extension, the degree and extension over FQ. And you look at this group as an additive group. There are two ways to start from an element in here and to go back to the base field. One is the norm and one is the trace. Okay, so this is something we would have seen in Galois theory, but let me just recall what it was in this case. So the norm is the product of the Galois conjugates, and that's exactly these. These are the Galois conjugates. X to the q, x to the q squared, and so on till x to the q to the n minus 1. And the trace is their sum, so that's just x to the q, and so on. So these are the roots of the minimal polynomial. Anyway, so we have these two ways to go from starting from here to go down. And if S is of size K, so I've still not told what, oh, I guess okay. Anyway, I think this is something I already mentioned. So if S is of size K, it's a K regular graph. Now, what is our S that we want to take? It's the set of all elements in the top field, which have norm 1. Okay, so I have FQ to the N here, I have FQ here, and I take the norm map. You look at all the X such that norm X equals to 1. Now, there are more than one way of taking norm. So sometimes, so of course, this is like a tower. So this Q is some power of P. So there is FP sitting below. And it could be that you might want to take the norm right to the base field, but in this talk, so initially I'll keep saying FQ to denote that I'm taking the norm only up to this intermediate field. But later on, I'll just say it as N for ease of notation, but I really mean just this. So we are never going to be talking about this base field. Okay. So it's for us, we're just talking about this extension. Okay. So if S has size K, then it's a K regular graph. But what is K? Okay. How do we, so we want to know the number of norm 1 elements in FQ to the N. It's an relatively easy exercise to show that this norm map is surjective. Okay, if you are given the fact that these two are cyclic groups, it is not hard to show that a generator of this cyclic group. So if you take alpha as FQ to the N cross, as a generator of FQ to the N cross, what will happen is norm of alpha will generate the cyclic group downstairs. Okay, and so this will tell you that this norm map is surjective, and then use the first isomorphism theorem. The kernel is a set of norm 1 elements, so the norm the size of the kernel is just the size of this group here divided by the size of the image here. Yeah, so it's just Q to the N minus 1 divided by Q minus 1. So great, we know the degree of this graph now. Okay, and I will denote N1 to be the norm 1 elements sitting inside FQ to the N. Okay, so all well and good. Now we want to know when the associated graph is directed or undirected. Okay, and we saw that that relies on the fact that whether your set you started with was a symmetric set or not. Okay, so it's undirected if it is symmetric, and otherwise it is directed. So now we want to know when will norm minus X be 1 for whenever X has norm 1, right? We want, so symmetric meant if X is in the set, you want minus X to be in the set, and something is in the set if it has norm 1. So that translates to you want to know when norm of minus X is 1. But norm is multiplicative, so it means that you're taking, so norm of minus X is the same as, oh, sorry. This is norm of minus 1 times norm of X. But we know this to be 1. So you're really asking when is norm 1 equal to 1. And if you have any element in the base field, then the norm is just, so if you have A here, norm of A is A to the N. Okay, so it's not just A itself, it will, the Galois conjugates are just itself, so it becomes A to the N. And so we're asking when minus 1 to the N is 1. Okay, so that's when it's even. So it's undirected if N is even, and it's a directed graph if N is odd. Okay, so we've understood a little more about our graphs. Now going to the spectrum, we want to know, okay, we had this very nice thing that whenever you have a finite abelian group, you can explicitly say what the eigenvalues are of the adjacency matrix, as long as you know what the characters of this group are. Okay, and in the finite field case, we understand them very well. Okay, so to start with, so we want to know the additive characters of fq to the n. But before that, it comes from below. So this whole tower that is always there. Okay, so but here we need to go all the way down. So you have fq to the n. You have fq. So this is the extension we're talking about. But this is some p to the r. Okay, so there's a prime subfield sitting inside underneath all this. That's like the ground level. Okay. We first need to understand what the characters of FP are, and then it's something like we will use that to construct the characters of these fields above. Okay, and the ones right below are just, so for each A in FP, you get a character in this form. Okay, so e to the 2 pi I by p, or you can write it as zeta if you want to see it's a primitive pth root of unity. Okay, so zeta zeta of, I mean, so if you take a not 0, and then it's just 1. But if you want the primitive roots, a will be not 0, and then it's just this for each. Okay, maybe zeta sub a of x. Okay, but it's, to me, I prefer seeing things explicitly, so I've written it as e to the 2 pi I ax over b. Okay, and if a is 0, this will mean chi a of x is 1, no matter what x is. So this is called a trivial character, and all other characters are said to be non-trivial. So these coming from a not equal to 0. Okay, now we jump to fq, which is fp to the r. So now you fix a non-trivial character. We have p minus 1 choices, and it won't really matter in the end. So but for purposes of when you write down to make things consistent, we fix 1, and we don't lose any generality in doing that. Okay, so if you fix chi to be any non-trivial character, then if you want a character up here, you take trace of ax, apply it to chi, and that will be what psi a of x is. Okay, so for each a, you have the character psi a, and what does psi a do? It takes x to chi of trace of ax. Okay, so in some sense, we're going back to this exponential here, except now see here, a is actually a number between 0 and p minus 1, so it's all fine. But when we are here, this is a finite field of which is not of it's not a prime field. So we need a way to go back down, and that's why you should expect something like the trace to come into the picture. Okay, that's why the trace of ax is coming, because ax itself won't sit inside won't be something that you can take exponential and find that it lands in C cross. Okay, so that's about here. But finally, we wanted to know what are the characters of fq to the n. So now we have to go one step higher, but the pattern is probably clear now. So now you fix a non-trivial character of fq, and then for each a and fq to the n, the characters are given by psi of a, where psi of a of x is just psi of t, trace of ax. Okay, so this is a trace. Yeah, I think when I introduced the trace notation, I just stuck to t, and so I've written t here. Okay, so from what we saw earlier, we know that the eigenvalues are given by summing the characters at the points which we've chosen to be our symmetric or maybe non-symmetric set, using which we are drawing the edges. Okay, so here in our case, it was the norm 1 elements. And so we say, okay, so we sum over psi a of x for each a. So you fix an a. So fix a. And fq and cross. Okay. Again, if you just take 0, you'll just get the 0 the trivial character. So we are looking at the others. So if you sum over the elements of norm 1, this by the definition is just psi of t trace of ax. Now I just do a change of variable here because I'm having norm x equal to 1, trace of ax. I can just change it to be sum over y, where you're taking trace of y, and norm y is b. So b being the trace of it. Sorry, norm of it. Okay, so y is basically ax. Okay, and so with this change of variable, I get this very nice simplified looking term. And these happen to be something that come in number theory. Okay, so this is what is known as a generalized Kloosterman sum, which is closely related to the classical Kloosterman sum. Why are we interested in that? It's because in number theory, whenever you have a sequence, so one area which is something I've studied a lot in my PhD thesis is equidistribution of sequences. So given a sequence, if suppose you know that they all lie in a fixed interval, you want to know how they are distributed. Okay, so similarly here, these Kloosterman sums, if you normalize them, you know that it lies in a certain interval. Okay, maybe I should write. Okay, so Kloosterman sum is you take x1 and so on till xn in fq, and you fix a non-trivial additive character, so character of fq, and you apply it to x1 plus x2 plus and so on till xn, where this satisfies the fact that the product is A. Okay, so this is the classical Kloosterman sum. Okay, but of course this looks very different from this thing here. Okay, but this is an example of a generalized Kloosterman sum. So maybe I say KL n of A. So this is nothing but, so you take the same additive character. So you're summing over T of X, trace of X, X belonging to not FQ, but you take the extension such that the norm of X is A. Okay, so they look quite similar, but here, there's this condition, the conditions are different. And Deligne proved that, in fact, these two are similar up to a sign. Okay, so Deligne showed that these are just -1 to the n minus 1, kn of it. Okay, so there's just a sign difference. So if you want to study either of them, since it's just a sign difference, you can, for example, now we're talking about all these values sitting inside some interval. So this one stays in -n. Or okay, we can normalize it to stay in -1, 1, for example. All of them lie in this interval. You want to know how it is distributed. But these seem to be too difficult to handle. But I can say something about these, and that's great because this is a symmetric interval. It doesn't matter. I can just add in all the negatives, and that won't affect the distribution. Okay, so you will see that it's and that's exactly what we do. So to study the classical Kloosterman sums, you okay, no, maybe I won't get into the number theory of it. But basically, once we know that these eigenvalues coming from the difference graphs are generalized Kloosterman sums, since we know the distribution of classical Kloosterman sums, this distribution is the same. Okay, maybe this might be a good place to pause, Soumya.
Yes, ma'am. Yes.
Okay, yeah, okay. So we shall reconvene in.
Yeah,